Okay, our last topic for the day is converting alcohols into halides. And we already know a couple ways to do this. Converting an OH group into a halogen, a bromine or a chlorine. Because we know that having bromines or chlorines are really useful in synthesis problems. So we already know some of the ways to do this, but we're going to learn some better ways, especially with the secondary alcohols. What I'm going to do is make a chart here because we can have different types of alcohols, primary, secondary, and tertiary. So depending on the type of alcohol, there are going to be better reagents to use to convert them into bromine and chlorine. Okay, so my alcohol can be primary, secondary, or tertiary. And then I'm going to list here the reagent to use to form a bromine. And then we'll make a column for the best reagent to use to form a chloride. So let's see, we've got primary, secondary, tertiary alcohol. So let's set up the rows of our chart. Primary alcohols, secondary alcohols, and tertiary alcohols. So if I have a primary alcohols work great in SN2 reactions. So these are all going to be SN2 reactions. They're all going to follow that SN2 mechanism where you don't want it to be sterically crowded, where you get backside attack and inversion of configuration. And we already learned in the SN2 chapter that HBr is a great reagent for forming a bromide because the hydrogen protonates the OH, it turns it into a good leaving group, and then the bromine can come in an SN2 reaction. But what we're going to see in this chapter is that there's another great reagent for doing this called PBr3, phosphorus tribromide. If we want to form a chloride, then we learned in the SN2 chapter that we could use HCl. What we didn't talk about there, because there was kind of a lot going on at the time, was that usually we throw in a catalyst. This catalyst is something that's known as a Lewis acid catalyst. And we'll go over why that's helpful in a minute. But there's also another reagent here that's really useful called SOCl2, thionyl chloride. And when we do this reaction, we usually throw in a little pyridine to pull off a proton in one of the steps. Okay, so two choices for each of those reactions. I'm going to skip down to the bottom now. If you have a tertiary alcohol, you definitely cannot do an SN2 type reaction because that alcohol is sterically crowded. So instead, all of these reactions are SN1 reactions. You form a carbocation as the key intermediate, and then your bromine or your chlorine comes in and adds to that. And we already learned the best reagent for each of these reactions. If you want to form a bromide, you use HBr. If you want to form a chloride, you use HCl. Same reagent as for the SN2 reaction, pretty much, but the difference is the mechanism. This proceeds through a carbocation intermediate, whereas these mechanisms are concerted. Now, if you have a secondary alcohol, we didn't really have a great reagent for that in the past, and from now on, when you want to do a reaction where you turn a secondary alcohol into a bromide, the best reagent to use is potassium tribromide. And if you want to make a chloride, the best reagent to use is thionyl chloride with a little pyridine mixed in. Okay, so this is the go-to chart when you're doing synthesis problems or trying to convert one reagent to another. This is going to tell you what the best reagent is to use to do those transformations. So now we're going to go over one or two of these mechanisms, but we do know a lot of the mechanisms. Like we already know the mechanisms for HBr and HCl. So we just have a few new ones here. We're going to talk about the mechanism for PBr3, the mechanism for SOCl2, and maybe we'll draw out this mechanism that we already know because it does have a Lewis acid catalyst in it. Okay, so let's clear our board and start drawing some mechanisms. Just a little bit more. Okay, so all mechanisms. They're all a little different from each other, but they all involve turning that terrible leaving group, OH, into a good leaving group. In the past, we've learned how to turn it into a tosylate, or we just protonate it and turn it into water. But now we have a couple other options here. So the new mechanisms in this chapter the first one I'll talk about is the one where we add HCl, but now we're adding an acid catalyst to it, a Lewis acid. This is called a Lewis acid. If you remember from general chemistry, a Lewis acid is an electron pair acceptor. So in this mechanism, let me just do this with a primary alcohol because that's usually when we use it. Zinc Cl2. So this is called a Lewis acid. It works the same way as other acids, basically. So instead of the OH getting protonated by the acidic proton in solution, it actually gets protonated by the Lewis acid. And we form this species here. So it acts the same way as if this had been a water molecule. This is a really good leaving group. It's a better leaving group than water. That's why we added the acid catalyst. This is a great leaving group. And so then the end of the reaction is just your normal backside attack with your nucleophile. So in this case, there were lots of chloride ions floating around. So that's going to attack and kick out our really good leaving group. And we get our chloride. Okay. If we're doing this kind of reaction with PBr3, let's jot that mechanism down. It's going to be the same idea. I'm going to turn that OH into a good leaving group. So PBr3, this is our second new mechanism that we haven't seen before. This time I'm going to use a secondary alcohol because PBr3 is really the best reagent to use for secondary alcohols. HBr and HCl don't really work in as high yield for secondary alcohols. So it's just the beginning of the mechanism that's a little new. You have your phosphorus tribromide. There are all these electronegative bromines on the phosphorus, so that phosphorus has a partial plus charge. So if something with 2 electrons is going to attack, it's going to attack this electrophilic center, and it'll kick out one of these bromines, which happens to be a good leaving group. It has an SN2-like look to it. And then what happens is that we get that product. And now once again, we have a really good leaving group. And so at this point, our nucleophile, which is a bromine, that bromine that got kicked out earlier, that makes a great nucleophile. It can do backside attack and kick out that great leaving group. So just like any other SN2 reaction, this is backside attack. And because it's an SN2 mechanism, we also see an inversion of configuration. So where I had a wedge here on this secondary carbon, that is now going to become a dash. Inversion of configuration happens. Okay, so that was PBr3. And then finally, the other new reagent that we have here is SOCl2. If we want to turn this secondary alcohol into a chloride, instead of a bromide. So this is the SOCl2 mechanism. Then again, it's just the beginning that starts out a little differently. So SOCl2 looks like this. It's a sulfur double bonded to an oxygen. It's got 2 chlorines on it. The oxygen, once again, is attracted to the species that has a partial plus charge, so that's the sulfur. So this comes in and attacks the sulfur, and in the mechanism, it actually kicks up a lone pair to the oxygen. And I'm just gonna, to save space here, I'm gonna erase a little bit of this so we have room to write. Okay, so this results in an oxygen that is now bonded to a sulfur. Let's see if my other pen is working better. That's attached to a sulfur. That's attached to an O dot dot minus. And right now there's 2 chlorines on here. Here's my oxygen. The oxygen still has a hydrogen, so that has a plus charge. And then what happens, it kind of reminds me of what you see in Grignard reactions sometimes when you have a good leaving group on here. This carbonyl-like double bond reforms and kicks out one of those chlorines because chlorine's a good leaving group. So we'll end up getting this. We still have an extra hydrogen on this oxygen. We have an oxygen, so this is a sulfur here, and a chlorine. And now the reason that pyridine was there, there's actually a little bit of pyridine in this mixture here. The reason that's there is to pull off the proton. Pyridine is just a good base. So our pyridine is going to pull off this proton, and we get down to this step here. Okay, and now we are set up with a really great leaving group again. I'm going to circle it. Here's our great leaving group. And so in our last step, our nucleophile is going to come in. It's going to do an SN2-like reaction with backside attack to kick out the leaving group. And this reaction is kind of neat. The reason this reagent is so special, as I draw this mechanism, maybe you'll see what's happening. It does backside attack on that alpha carbon. But what happens is it kicks this over and forms a double bond to sulfur and kicks out the chlorine as the leaving group. And so we actually make a little sulfur dioxide molecule here. This SO2 molecule is going to form. So what we end up getting, our main product, our substrate, is going to have an inversion of configuration because this was SN2. Okay, so our wedge switched to a dash. And then the side products, one of them is a gas, sulfur dioxide gas, and then our Cl- leaving group. But anytime you form a gas in a reaction, it's driven off into the atmosphere, and so that's a good driving force for the reaction. It disappears, Le Chatelier's principle pushes the equilibrium to the product side, and so you get a pretty good yield. And also you don't have to purify away a gas, it just bubbles out on its own. So that's why this gives really good yields of turning secondary alcohols into secondary chlorides. Okay, so those are our mechanisms. So now it is time to try problem 6 on the worksheet. So why don't you take a minute, pause the video, see what you can come up with for all of those different reactions. It's one, instead of telling me what forms, you're supplying the best reagent. And as you do that, I'll clean off the board and put my answers up here. Okay, so number 6. Oh, I should have told you this before you pause the video, but there's actually a typo on letter A. Otherwise, this problem becomes really hard to solve. You might have noticed some confusion with the stereochemistry. So it starts out with a dash to an OH group, and there's a wedge over here. And you're supposed to figure out what reagent to turn this into, this molecule over here. So on your paper, there's a typo. On your paper, I think this was written as a dash. It should have been written as a wedge. And that should be like that. So that probably makes the problem a lot easier. So in this case, the thing to notice is to identify the type of alcohol here. we have a secondary alcohol, not a primary or tertiary alcohol. So that means that the best reagent in our little chart that we made of what's the best reagent to use, thionyl chloride, SOCl2 with a little bit of pyridine, would be the best choice. And that will give us an inversion of configuration. We're asked to identify the mechanism, so this would be an SN2 mechanism. We just wrote that mechanism a few minutes ago. And then in letter B, now we're turning a primary alcohol into a primary chloride. So if we look at our chart that we made, we actually have two good reagents that would work here. Because this is a primary alcohol, we're going to proceed through an SN2 mechanism. So we have a choice of using HCl with a little bit of zinc chloride as our Lewis acid catalyst. Or we could have used the thionyl chloride again. That would work equally well. Thionyl chloride with pyridine. So we have two choices there. Let's see, letter C. I'm going to raise A up here and put C in. So letter C. We are turning this tertiary alcohol into a tertiary bromide. So tertiary alcohol means that it's too sterically crowded to do an SN2 reaction, and so I have to proceed via an SN1 reaction. And if I look at the little chart we made of what the best reagent is to use here, it's going to be HBr. Our mechanism, if we were writing it out, would be to protonate the OH to turn it into a good leaving group. That pops off and makes a carbocation intermediate, SN1 mechanism, and then the bromine comes in and attaches. Okay, so that's our best reagent in C. And then in D, we actually have, this is not meant to be a typo in D. We have something funny happening with the stereochemistry here. So we have a wedge with our OH at that chirality center, and we want to turn this into a chloride, but we want it to remain a wedge. And so since this is a secondary alcohol, the normal way to do this is with thionyl chloride, SOCl2, but that would give an inversion of configuration. So if we want to not have an inversion of configuration, what we actually have to do is do two SN2 reactions back to back. So for example, we could use PBr3, and that would flip this from a wedge to a dash. That would be a Br. And then I want to flip it back again, but by using PBr3, I've turned this into a good leaving group, so I can still do an SN2 reaction on that. And I would just want to make sure I use conditions that are going to give an SN2 product, not an E2 product. So using something that's a good nucleophile, like sodium chloride, and then maybe putting in some acetone or DMSO solvent, something that's a polar aprotic solvent that would help speed up an SN2 reaction. So what's happening here is that you have two SN2 reactions back to back. So first you invert the configuration once and then you invert it back. But that's really the only way to try and get to this product where you have a wedge if you start it with a wedge. Okay, I think we'll end there today. 7 you can try on your own. It's kind of an interesting problem, but the solutions will be online on Canvas.